So this is coordinate system and mapping now. The next thing we need to learn is understanding coordinate systems and map projections. The learning sequence is coordinate systems and map projections, coordinates and coordinate systems, map projections, developable surfaces, map projection parameters, map projection properties, determining deformation and its distribution. So datum, we will see what a datum is. We talk about datums, and I think everybody here should be familiar with WGS 84. And NAT 27 and NAT 83 are North American datum, which we use back home. And this course was developed for the States, so that's why we have it there. But for Mongolia, we really don't care. We just want to worry about WGS 84. What is a datum? So why we're talking about datum is we're talking about the Earth is round or ellipsoid. We need to know where the center of the Earth is. Yeah? So in the past, in Mongolia, you had things like Gauss-Kruger and all that stuff. So that's geodesy, right? This is the study of the shape of the Earth. And the geodesies like Gauss-Kruger and some of these other ones are somewhere in the center, but it's not where it is, because the Earth is not a perfect sphere, and it is not homogeneous in material. And depending on where you pick the center of the Earth, then you could have a different axis. And with each different axis or location of the center of the Earth, your location, your lat-long location will change. So that's why it's very confusing. If you have maps and they have different datums and projections, then you have different coordinates for the same place. To come back to WGS 84, WGS 84 is the center of mass of the Earth. Center of mass of the Earth, which, because we're using satellites, GPS satellites and GNSS satellites, so the satellites rotate around the center of mass of the Earth, and this is where WGS 84 datum is located. NAT 83 and NAT 27 is very, very close to WGS 84. The Canadians and Americans just changed it a little bit because they wanted to make it a little more precise for Canada and US. The difference between, in Canada, if I use NAT 83 or WGS 84, is only a few centimeters. But the geodesists are very fussy, so they want the few centimeter accuracy. But in Mongolia, you have adopted WGS 84, okay? Which is the center of mass that the satellites fly around. So when you use GPS, it uses WGS 84 as the same center point of the Earth. Spherical coordinates is 3D only. Do not ignore curvature of the Earth. Uses two angles of rotation, latitude and longitude, and radius to specify locations. So your measure east-west varies from 180 degrees east to 180 degrees west. So this is the curve, okay? So longitude goes 180 degrees. This arc. Sorry, 180 degrees all the way. It's looking from the North Pole. This is North Pole down. So 0 to 180 degrees. Okay, so this is central meridian. 0, so you go. So that's west. That's east. Okay? So from 0 to 180. And if this is the north and south, so the latitude goes from 0 to 90. All the way up. Okay? So this is the latitude, 45 degrees. 0 to 90 degrees north, 0 to 90 degrees south. So generally, in convention, in Mongolia, you're over here, so you're about 90-something degrees west. Yeah? In Canada, we're minus. You display the longitude and latitude in degrees, minutes, and seconds, or decimal degrees. Okay, so 2D coordinate system, you have basically X and Y in a flat plane. Okay, so GIS data typically uses Cartesian system for simplicity, which is the 2D system. And GIS normally ignores the curvature of the Earth. For small areas, that's okay. So in local areas, we treat the ground as flat. Okay? In the US, they use state plane. In the rest of the world, we basically use UTM. So the UTM system is where you take the world and you break it up into 6-degree strips. The UTM is a transverse Mercator. I'll show some other examples as well. So what we're doing is we know the world is 360 degrees if you go around the circumference. If you break it up, you can have 60 UTM zones. And in Mongolia, I think you have about 5 UTM zones. And really, the UTM system was developed for military use, for military maps, okay? Topographic military maps. And we'll go into that a little more detail. Yeah. So map projection. The Earth is basically an ellipsoid, which is really not a sphere, but it's slightly flat on the top and the bottom, and it's kind of bumpy. In order to generate a map, a flat map, we need to project from the curve to a flat plane. So this is the Earth, which is an ellipsoid, and we want to create a flat map surface. So we need to project. This point goes to here, this point goes to here, this point goes to here. And that is what we call projection. And there are different kinds of projections. Okay, this is just a plane projection. So generally, we're dealing with cylindrical. So this is what we call the Mercator. It's the cylindrical projection. And the transverse Mercator is when you turn the cylinder horizontally. This is the cylinder, and this is the Earth inside the cylinder. And the other projection, the conical projection, is like an Albers projection. It's a conical projection. You use that for a big area in the north, mainly. But we won't bother with that. Central meridian. 0 degrees latitude is the prime meridian. In terms of the UTM, we have 6 degrees. In Mongolia, say zone 47, which is the zone east of UB. Zone 47, for example, the central meridian is 99 degrees. Okay, that's the central meridian for zone 47. Okay, so the meridian that defines the center of the projection. So for the UTM zone 47, the center is 99 degrees, and that is the central meridian. Okay, and the latitude of origin defines the center of the projection. Usually the latitude of origin is normally the equator. So your y-axis measures 0 at the equator and then so many meters north. Now, it does not have to be the equator. In Colombia, they offset this by 1 million, I think. But for UTM, the latitude of origin is 0 at the equator. And when you look at UTM coordinates for Mongolia, the y coordinate, the y value is the number of meters from the equator. Projections are also related to the light sources. So the genomic, probably the one I think we're using. So there's 3 types. There's genomic, stereographic, and orthographic light sources. Yeah. So the stereographic is from the other side of the Earth, and orthographic is infinite from the sun. The property of map projection. So area, shape, distance, direction. All maps contain areas because we're going from 3D to 2D transformation. Different types of map projections, so major properties, area, and shape. What it means is that if you project a map from a curve to a flat, if you want to keep the area the same, then the shape changes. If you want to keep the shape, then the area changes. You can't keep the area and the shape the same. So that's the major properties. And the minor properties is distance and direction, and they can coexist, but not everywhere on the map. Keep the distance and direction in certain small areas, but not on the whole map. That really means that there is distortion when you go from curved to flat. There's going to be distortion and warping, so you can't keep everything the same. So for example, in terms of distortion of a map, when you project, you can never have all of these holding true. Like you cannot have direction, distance, area, and shape all transformed equally. These are different types of projection. So if you want to have equal area map projection, it is a projection that keeps the area from the curve to the flat. And in order to preserve the area, the meridians and parallels are not at right angles. The distance distortion is always present, and the shape is often skewed. The meridian and parallels are not at right angles. The meridian and the parallel should be always perpendicular, but if you want to keep area, they won't be. Cylindrical equal area map projection. So it keeps the area correct, but then it compresses. So you can see that because it stretches in the north, it's wider. So to keep the area correct, then the latitudes have to compress. Say North Canada, the same area. As you go north, Canada gets wider. And in order to keep the same area, the latitudes have to be compressed. This is a second example of equal area. The two areas for Canada is the same, but in order to keep the area the same, so either you compress the latitude or you have to compress the longitude. In this case, you're compressing the longitude. Conformal map projection is also an orthomorphic, okay? Preserves angles around points and shape of small areas. So the goal is to preserve angles around points and shapes of small areas, same scale in all directions, from or to a point. This is what happens with the projection. So this is called the Mercator projection. So this is probably the most famous projection. Keeps the latitude and longitude perpendicular. Equidistant map projection, I won't worry about that. So this just keeps the distances correct. Azimuthal map projection. This preserves direction from one point to the other point. We don't use these projections, so we won't. This is for information. Okay. These are the different combination of projections. This is the Robinson one. So this is another one that's quite common. You see this a lot for the world.